20-1, Chapter 7. We've talked absolute values, graphing piecewise of them, solving absolute value equations. Well, now we kind of take a hard left turn, and the rest of this chapter, which is just like one lesson, reciprocal functions. So absolute values, we talked about uniqueness of graphs, of absolute functions. Remember, if you have a graph that's just a regular graph, the absolute of that, if we have y is equal to f at x, well, the absolute of that, if you recalled, the absolute graph means we can't have any y's in negatives. We have to have positives. So we would have the bounce point there, and then the graph, the absolute graph would only be positive y's, nothing down in the negatives. Well, reciprocal functions is going to be all about graphing as well. This will focus on graphs as well, but different kind of graph. Math, nothing new. Not a lot of calculation. Terminology and some memory stuff, absolutely. Note reciprocal. Probably the most common place you've seen reciprocals is really with fractions. If we have a over b, the reciprocal is the flipped version of it, b over a. But what we're going to focus on is if I just have a single value, if I had like a z, well, the reciprocal of z, because it's like z over 1, will be the reciprocal 1 over z. And we're going to be looking at these sorts of forms of what does a reciprocal function look like as a graph compared to just the function graphed. Well, what that means is we are normally used to having a function y equal to f at x, but what we're going to do is the reciprocal of it. So we're going to want 1 over f at x. And this is a graph, a type of graph that really follows a pattern for what we're looking at. So some terminology, how it applies to get the graph of a function, but then it's reciprocal. And the key here is it's the y value equals f at x. The reciprocal is 1 over f at x. So our x values stay the same. But whatever our y value is in the function for y equals f at x, we're now going to have the y value, instead of being y, it'll be 1 over. Actually, that should be a y, 1 over the y. So that's what we're looking at doing. You'll see as we look at some examples. A little different, a little quirky, but manageable. So this first example on page 15 says we want to graph y equal to f at x, and we want to graph the reciprocal of it. Well, we're starting with f at x equal to x. So we're going to graph the fact that y equals f at x is just the x value. Y equals x. Not real complicated graph, but then we're going to graph y equals, and f at x equals x, we're going to graph 1 over x. So you have one big table of values there. I split it into the two table of values. We have the table of values where we have x, and we want to graph y equal to x. Well, that third column is kind of what I've done here, and I've created it then having x and graphing the reciprocal of it. So let's just first focus on those first two columns and graphing just the y equal to x graph. So to finish up, or to input into my table of values, x equals -5. So if y equals x, y will equal -5. X equals -2, y will equal -2. Not overly complicated. This is the set of ordered pairs we want to look at. Obviously, special values have been put into it to help with the graph, these halves and tenths and things, but there's what I want to graph. Our first point is -5, -5. So at -5, -5, graph it. So just do this and create this graph. See what you come up with. -2, -2, -1, -1. -1/2, -1/2, -1/5, -1/5. 1/10, 1/10, 0, 0. We're going to get a whole bunch. Because of this half, fifths, tenths, and things, it's going to be pretty squished in there, but do the best you can. 1/10, 1/10, 1/5, 1/5, 1/2, 1/2, 1, 1, 2, 2, 5, 5. So what do we end up with here? Well, let's see how I can do this freehand, but we end up with a straight line graph. All those points form a straight line. There's our y equal to f at x graph. Now, we want to graph the reciprocal. So reciprocal means we want to flip the numerator denominator. And in this case, if we had y equals x, our reciprocal is now y equals 1 over x. So if I had x is -5, flip that, y will be -1/5. -2, flip that, -1/2. -1, flip that, just -1 over 1, which is -1. -1/2, when I reciprocate, becomes -2 over 1 or -2. -1/5, reciprocated, becomes -5 over 1 or -5. -10. 0 over 1, when I reciprocate, becomes 1 over 0. But this is an important one, because a denominator of 0 doesn't exist. This is undefined. So when x equals 0, it's undefined. Nothing else works for y. We'll see that in our graph. 1/10, when I reciprocate, 10 over 1 or 10. 1/5 is 5 over 1 or 5. 2, 1 reciprocated becomes 1 over 1 or 1. 2 reciprocated becomes 1/2. 5 becomes 1/5. So now I need to graph this second function, which is the reciprocal function. So I need to graph the first point, which is x -5, y -1/5. So -5, -1/5. Kind of hard to draw in a -1/5, but do the best you can. -2 is at -1/2. -1 is at -1. -1/2 is at -2. -1/5 is at -5. So there's my first bit. My 0, or sorry, -1/10, sorry about that, -1/10 goes down to -10, so right beside. Well, and we did have actually, that's good. So there's the first few points. Well, I can see a couple things that are different. Well, here this -10, -1/10, -10, I'm not on the axis yet, but I'm close to it. And we can see we slowly move away from it. So if I were to connect these points, I'm slowly moving away from the axis and then going through the points, but then I'm going back towards the x-axis. Well, what would happen if I had x equal to, let's just add a -10 here. If I was at x -10, I would be at -1/10. So -10, -1/10. Again, I'm getting close to the axis, but never actually getting to it yet. Well, let's do the bottom half now. Finish it off. 1/10 gives me 10. 1/5, 5. 1/2, 2, 1, 1. And then I'm at 2, which is a half. 5, which is 1/5. And if I want to, let's do x at 10, which would give me y. The reciprocal of that would be 1/10. So 10 and then 1/10. So again, I'm not touching the x or the y-axis. I can connect these points slowly on a curve, and then I go through and I get to my 1/10, but never actually get to that x-axis again. So we see a bit of a pattern developing there, and there's our reciprocal graph. Now the reciprocal graphs will always look like that. That's not a coincidence, that's not lucky. You're gonna see the same kind of thing. But what's important is some of the terminology and how we can come up with the reciprocal graph. We can see it by graphing it, but I don't want to have to graph that many points every time. So let's look at some of the key components of the graph on page 16. To start with, this terminology is important. We have things that are called asymptotes. And asymptotes are lines that curve graph's approach but never intersect. And we saw that as we went through it. Well, we have vertical asymptotes. If we go to our graph, our vertical asymptote, what were we approaching vertically but never hit? Well, our vertical asymptote was we were approaching the y-axis, and we got to like 1/10 down here and 1/10 close to it up there, but never got to it. So is it always going to be like that? Well, yeah, it is. Vertical asymptotes occur at NPVs of a function. NPVs cannot occur. Therefore, they can't be part of a graph. In this case, for our reciprocal graph, we had y equals 1 over x. Well, what's the NPV here? Well, what can we not have in the denominator? We can't have 0, which means our x cannot equal 0. So the NPV, or in this case, the NPV, the asymptote has an equation of x equal to 0, because that's what our NPV is. The asymptote occurs at x equal to 0. So at x equal to 0, where we don't move left or right, at x0, there's the vertical asymptote that we will never ever touch. Because even if I thought about it, if I have an x value of 100, or let's go 1,000. If I was at x 1,000, sorry, not 1,000, because that's different asymptote, my bad, sorry. If x were 1,000th, so if I was at 1,000th, so close, barely off of it, 1,000th over, my y value, the reciprocal, would be 1,000. So I would be way, way up. So at y equal 1,000, I would be almost touching, but not. You will never touch, contact the vertical asymptote. So the vertical asymptote, one thing you will never touch is where the NPVs occur. Now the other part to that is if y equaled 1 over x, the original function was y equal to x. Our NPV could also be thought of as just your x-intercept for the regular function. Our x-intercept occurs when y is 0. If y is 0, x equals 0 as well. So x equals 0, whether it's the NPV or the x-intercept. That's our vertical asymptote. Our horizontal asymptote for this year will always be the x-axis, because very large and very small values of x approach 0 but never get there. So if we take a look at that, if I take a look for my y equals 1 over x reciprocal function, big values of x. If I said x equaled, again, let's go to 1,000. If I said x equaled 1,000, well, 1 over x, my y value, would be 1,000th. So at x equal to 1,000, which would be way, way, way over here, well, my y value would be 1,000th. It would be barely off the axis. My graph would constantly get closer and closer and closer and closer, but never ever come in contact. So for us, horizontal asymptotes will always be the x-axis for that reason. So asymptotes, lines that get approached but don't intersect. Horizontal asymptote this year will always be the x-axis, but the key is the vertical asymptote will be your NPV of the reciprocal function or your x-intercept of your regular function. They're the same thing. Now the second thing are your invariant points. Invariant points we talked about with the absolute are points that are the same on a graph, and in this case, it's reciprocal. And this year, invariant points always occur where y is equal to 1 and y equals -1. So let's take a look at the graph. We can see that a y value of 1 meant our x was 1, so we had that point. And at y -1, we had that point. And that point, we can see, was the same point on both graphs. At y equal to 1, wherever one graph has a point, the reciprocal will also. At y equals -1, where one graph has the point, the reciprocal graph will also have a point. It's the only time these two graphs will intersect, where y equals 1 and y equals -1. So we can identify invariant points by solving for x values. Whatever it is, whatever function you have, if y equals 3x plus 4, I know if I said that y equaled 1, I'm just making this one up, but if y equaled 3x plus 4, and I said y equals 1, and I solved for x, subtract 4, divide by 3, -4/3. That means at -4/3 x and y1, that point would be for the regular graph, but that point would also be for the reciprocal graph. Where y equals 1, that is going to be the point on both the function and the reciprocal function. So you'll see it probably better as we work through examples, but asymptotes and invariant points are key for doing these graphs. So there's kind of 5 steps to graphing reciprocal functions. We want to identify the function and its reciprocal function. See them both. That's a quick little step, but it's important. We then want to identify the vertical asymptotes. These are our x-intercepts for the function or our NPVs of the reciprocal function. They're the same thing, but we need the vertical asymptotes because our graph will not cross here. The other thing we need to determine are the invariant points, like I just said. We need the coordinates. What's the x value when y equals 1? What's the x value when y equals -1? We will get ordered pairs, something 1, something -1. These are the points that both graphs will intersect with. The fourth thing is to graph the original function. if it asks for it. If it's linear, we can use the y equals mx plus b. If it's a quadratic, the vertex form. Stuff you've seen in the past. That graphs the original function, but then we can graph the reciprocal function by using all of this above information to compare. It all ties together. So let's take a look at an example. Page 18, we're given f at x equal to 3x plus 6. So we want to graph it, and we want to graph its reciprocal. So what's the reciprocal function? It's the first thing it asked. Well, the reciprocal function would be y equal to 1 over 3x plus 6. Because y equals 3x plus 6, that's our function. And y equals 1 over 3x plus 6, there's our reciprocal function. So there's step 1. Step 2, or B in the notes, the vertical asymptote. Well, the vertical asymptote occurs at the NPV value. Well, if I take a look, what's my NPV? My NPV occurs, because I don't want my denominator to be 0, the NPV will be when 0 is equal to 3x plus 6. Because we don't want 3x plus 6 to be 0, so what's the x value that does that? Subtract 6 from both sides, divide by 3. And in this case, our asymptote occurs where x equals negative 2. So at x equal to negative 2, there's the equation of our vertical asymptote. I'm going to put that on my graph right now. Where x equals negative 2, I know x equals negative 2. That vertical line, because that's my NPV, that is not, that's a line that my graph will not cross at all, the vertical asymptote. We also know, because it happens for every time, it doesn't really ask for it, but remember the horizontal asymptote this year, for the graphs that we're going to do, will always be the x-axis. So those are the two lines, a vertical and a horizontal, that our graph will not, our reciprocal graph will not cross. Part C is to determine the invariant points. Well, invariant points occur where y is equal to 1 and where y is equal to negative 1. Now, it's the same in both graphs. Remember, invariant points happen on the reciprocal graph and on the regular function. So I'm going to work with the regular function. It's easier to work with. First possibility, when y is equal to 1, what's the x value? Subtract 6 from both sides. Negative 5 equals 3x. Sorry, 3x, divide by 3. X is negative 5. So we know at negative 5, sorry, it's negative 5/3. We know at negative 5/3, our y value is 1. So when y is 1, x is negative 5/3. Well, the second invariant point happens when y is negative 1 for our function 3x plus 6. Subtract 6. Negative 7 equals 3x. Divide by 3. We get x equal to negative 7/3. So we know at negative 7/3, our y value is negative 1. So there's 2 points that our graph has to intersect with. Now, negative 5/3, I have to graph that. Let's put it into a little bit easier terms. That would be negative 1 and 2/3. That's what we're looking at. Negative 1 and 2/3, 1. So at -1 and 2/3, -1 and 2/3, we're at +1. There you go. There's -5/3 and 1. -1 and 2/3 and 1. There's one invariant point. Our second invariant point happens at -7/3, which is -2 and 1/3, -1. So at -2 and 1/3, -1, we have another invariant point. Those are the 2 points that both of our graphs have to pass through. So now what are we going to do? Now we're going to graph the 2 functions. So I'm going to graph the first regular function to start. Y equals 3x plus 6. Well, going back to linear equations, our b value is 6 and our slope is 3/1. So b value is 6, slope is 3/1, or that's the same as having -3/-1, 3 down, 1 to the left. 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 So there's our points for our y equals f at x function. There's y equals 3x plus 6. We see that we're passing through our 2 invariant points. Now, if I had a straight edge, it would be a little bit closer there, but it's pretty close. And now if I want to graph the reciprocal, well, I don't want a whole bunch of points, but what I can do is use this information. To graph the reciprocal, I know that I have to pass through the 2 invariant points. I also know that I can't cross my asymptotes. So I know that I'm going to go through my invariant points, and I'm going to get closer to the asymptotes the further I get from the origin, but I'll never truly contact them. Down below, I would be close to the axes, my asymptotes, go through the invariant points, and then continue and get closer and closer to the asymptote. And there's my graph. The red is my reciprocal because I'm not contacting the asymptotes and I am going through my 2 invariant points. There's how I can come up with a reciprocal graph. Lots of little calculations that aren't new and being able to apply them to see what our function and its reciprocal function look like on a graph. Page 19, it's the same kind of thing, but now we have a quadratic, so it's going to change things. Here we go. First thing, function, y equals x squared minus 4, and the reciprocal will be 1 over x squared minus 4. There's the first thing we need. Second thing is we need the asymptotes. Well, asymptotes occur at the NPV. Well, NPV is if x squared minus 4 equals 0. Well, that's the same as what our x-intercept would be at if y equals 0. So it's the same. But for the asymptotes then, 0 equal to x squared minus 4. I want to identify what those values are. So what do? Add 4 to both sides. X squared by itself, square root both sides. So we get x, but because I square rooted, I need the positive and the negative of root 4, which is positive or negative 2. So at x equal to positive and negative 2, there's my asymptotes. What's different is when we have a quadratic, we end up with multiple asymptotes. So at x equal to positive 2 and x equal to negative 2, we get asymptotes. Positive 2 and x equal to negative 2. There's our asymptotes. We have 2 asymptotes to consider in this graph. Well, here we go. Next part, C, are the invariant points. I need the points that both graphs go through. All right, how do we get invariant points? Well, invariant points occur when y equals 1. Let's start there. So, y equals 1 for x squared minus 4. So what do I need to do? Add 4 to both sides. We get 5 equal to x squared. Square root both sides, and when we square root both sides, we need to consider the positive and the negative of our root. So x is equal to positive and negative root 5. Now we need to put these points on a graph, so having a bit of a decimal equivalent there will be helpful. If we use our calculator, we're going to get positive and negative root 5, which is positive and negative 2.24 roughly. So about 2 1/4. We're not going to be perfect on our graph, but it'll be close. So that means 2 of our invariant points would be positive 2.24 when the y value is 1. Don't forget, I create ordered pairs for my invariant points. There's x for y1. The other x is negative 2.24 when y is 1. So I have 2 invariant points so far. Well, now I need the invariant points as well, because invariant points also occur when y is negative 1. So what do? Here we go. Y is negative 1 for x squared minus 4. Add 4 to both sides. 3 equals x squared. I have to square root both sides, which means I have x, and I have the positive and negative of root 3. Well, again, because I want to graph it, I can calculate root 3, which would be approximately positive or negative 1.73 is x. So that tells me my other invariant points will be 1.73 when y is negative 1, or negative 1.73 when y is negative 1. So we have 4 invariant points to add to our graph. So now I need to add those invariant points to my graph. I just want to make this a little smaller so it's easier to see. So what are my invariant points? 2.24, so 2 1/4 roughly, positive 1. There's 1 invariant point. And it's not going to be absolutely perfect, I get it, because it's so small, but we can get a pretty good idea. We also have negative 2.24 at y equal to 1. So there's 2 of the invariant points. I also had these 2 invariant points, 1.73 at negative 1 and negative 1.73 at negative 1. So there's the 4 invariant points that we now have on our graph. Well, what's our last step now, D, is I want to graph the 2 functions. Well, the last thing to do is I want to be able to graph y equals x squared minus 4. So I'm just going to, how would I graph y equals x squared minus 4? Well, if I have y equals x squared minus 4, vertex form helps. So we have to use vertex form again. What do I do for vertex form? I want to get, well, in this case, x squared minus 4, there's my form. If I have x squared minus 4, remember it's a bracket x minus p squared plus q. Well, what's the a value out in front? It's 1. So that's not a big deal. But x is by itself, so what would my p be? What have I done with the x? I've subtracted 0. So my vertex is 0, and what's my q? My q is negative 4. My vertex is 0, negative 4. My a value is positive 1, so I know that I open up. So 0, negative 4 for a vertex, opening up, 0, -4 was my vertex for my y equals f at x function, y equals x squared minus 4. It opens up, but the other thing I know is it has to pass through the invariant points. So I have those 4 points. The asymptote is not a problem because the asymptote is for my reciprocal graph. For my function, my graph needs to pass through the invariance, hit my vertex, pass through invariance. So that's my y equals x squared minus 4 graph. But I still need to finish my graph for the reciprocal. Well, what's important with the reciprocal graph? I can't cross the asymptotes. I have to go through these points. So when it's a quadratic, we actually have 3 parts. I need to go through that invariant point, but not hit my asymptotes. So I'm approaching my asymptotes, but not contacting. It'll look similar on the right side. Approaching asymptotes, going through the invariant point, but not contacting the asymptotes. And remember, our x-axis is also an asymptote, so these 2 points down here, I don't want to touch or contact my asymptotes, but I need to approach them, and I need to go through my invariant points. Wow, so there's the reciprocal of x squared minus 4. Going through the asymptotes, hitting the invariant points, and those are the graphs we end up with. Again, unique, tricky, different, not a lot of new math, but you have to think a bit. So, 4 more quick examples to do. I know it's a bit of a long video, lots of little bits of information. So that's how we can graph functions and the reciprocal functions, the pieces you need. Well, sometimes you're asked to just create one of them given a graph. We're always considering asymptotes and invariant points. So this question says we have the graph y equals x minus 4. We want the reciprocal, which is 1 over x minus 4. Well, where do asymptotes occur at? They occur at the NPVs, but the NPVs are also, NPV would be for x minus 4, it's also our x-intercept. X-intercept occurs where y equals 0. So if I have a graph, I don't even have to do a calculation. NPVs or x-intercept. We see where that happens. Our NPV, our x-intercept is here at x equal to 4. So I know my asymptote for my reciprocal graph happens there. I don't technically have to do any calculations. I know the x-intercept is the asymptote x equals 4. So there's a big chunk of it already done. And my invariant points. Invariant points happen where y equals 1 or y equals -1. So if I look on my graph, here's y equal to 1, here's y equal to -1. Well, when y equals 1, there's where my function occurs at y equal to 1. Here's where my function occurs at y equal to -1. So those are the 2 points that my reciprocal has to go through as well. At y equal to 1, there's the graph point. At y equals -1, there's the graph point. And that has to be the same on my reciprocal. So now I have everything in place. Don't hit your asymptotes. Go through the invariant points. So here, well, that's not great. Here, try it one more time. I'll understand. It's got to be decent, but not perfect. I went through my invariant point and didn't hit my asymptotes, but approached them. Here, go through my invariant point and approach my asymptotes, but don't go through them. The asymptote isn't always your y-axis. It's wherever you have your x-intercept. So there it is. Consider asymptotes, consider invariant points. Next one, maybe you want to give it a try. We don't even have a function here. We just have the graph of it. Give it a try, what we just talked about. See what you come up with. So what do we need to consider? Well, the first thing we need to consider, the asymptotes. It occurs at the x-intercept of our function. Well, we have our function here, and here's our x-intercept, so there's our asymptote. It's that simple. The x-intercept, x equals -1. There's the equation of the asymptote. X equal to -1. Can't go through x equal to -1. Our invariant points, again, happen where y equals 1 or y equals -1. So when y is 1, well, there it is. On this graph, there's y equal to 1. At y equals -1 on this graph, there's our point there. So here's the point on our function where y is equal to -1. Here's the point on our function when y equals 1. Those points, our reciprocal graph has to go through. So now we graph. How do I graph? Go through those points. Do not go through the asymptotes. So, close to my asymptote, to the invariant point, through the invariant point, and then curve and approach the next asymptote, but don't contact it. Don't contact the asymptote through the invariant points, down and approaching my asymptote, but never crossing it. We don't even need a function. If we have the graph will identify our asymptotes and our invariant points. And that's what we need. Page 21. Question 3. Given the graph, draw the reciprocal. Well, now we have a quadratic. So remember the quadratic, a little bit more involved. Our quadratic, we had 2 asymptotes. We had 4 invariant points. So that's what we need to consider. So here we go. Asymptotes occur at the x-intercepts. So where are the x-intercepts for our graph? Well, I'm not sure exactly what it is. It's about -4.8 maybe, and at 4.8. So there is where I want to draw my asymptotes. Not on -5, but almost at -5. Not on 5, but at like 4.8, almost at 5. There's the asymptotes because that's the x-intercept, which is also our NPVs. Now we need invariant points. Invariant points occur when y is 1 and y equals -1. So when I look at the initial quadratic, when y equals 1, where do we hit the graph? We hit it there, and we hit it there. So those 2 points have to have my reciprocal graph go through it. But invariant points also occur when y is -1. So at y -1, there's where my graph is, there's where my graph is. So I need to create my reciprocal graph considering not to intersect my asymptotes, and I have to go through my invariant points. Well, remember, we got 3 parts. Here's my middle part. In this case, I don't want to contact my x-axis because that's an asymptote, and I want to be close to but never contact my asymptote that's vertical. But I have the outside parts, close to but never contacting the asymptote, through the invariant point, curving, and then approaching the asymptote. And the same thing on the outside here. Never touching the asymptote, through the invariant point, curling, never touching the asymptote. So sometimes you're given the information and you need to come up with, you have to calculate the intercepts and things and the invariant points. But sometimes you're just given a graph and saying, hey, do you understand what everything means? Last one, give it a try, see what you come up with, and then we'll compare. Graph the reciprocal of y equals -1/4 bracket x minus 2 squared plus 4. See what you get. Here we go, one more time. Asymptotes occur at our x-intercepts. Where are our x-intercepts? Well, it looks in this case, our x-intercepts are right on x equal to 6 and x equal to 2, -2, sorry. So there's our x-intercepts, so that's where our asymptotes are. Can't cross those two vertical lines. Invariant points. Invariant points occur where y is 1 and y is -1. So when y is 1, our initial function is there at y1 and there at y equal to 1. Our invariant points when y is -1, there's our graph at y -1, and there's another point where our graph is when y is -1. So what's different this time is that our inner invariant points are above the x-axis. Doesn't matter. We still don't want to contact the asymptote. Whoops, different color just to be consistent. We don't want to touch the asymptote. We want to go through the invariant point curve. Remember, the x-axis is always an asymptote. We can't cross it, approach it, but then we move away through the invariant point and moving up, but never hitting our second asymptote. As long as the graph is relatively neat and tidy, it's acceptable. Doesn't have to be perfect. You can see mine's not. Not finished though, because I still have an invariant point here. Can't cross the asymptote that's my x-axis. Can't cross the asymptote that's x equal to -2. Have to go through the invariant point, but can't hit the asymptote at x equals 6. And I can't cross the asymptote, which is my x-axis. So there you go. Lots of information, not a ton of difficult math. It's just understanding where asymptotes and invariant points are, how you can calculate them, and now how you can graph them. So assignment, textbook. Page 403 to 405. I double-checked the pages. I apologize for the lesson the other day. So there's your questions. Don't forget there are Cartesian grids if you want to print some off. It's a little nicer to have the Cartesian grids. They're in the worksheet section of the Google class. There's your assignment. It's a little different. Give it a whirl. Practice this. It's different. Have fun with it.